All right, so we talked about relativistic velocity. And so what about relativistic momentum? Because we know that we define momentum in the classical way as mass times velocity. So what's going to happen to our definition of momentum when we are looking at relativistic objects? And so you may recall that when we were looking at the addition of velocities, considering relativistic objects, we're looking at a rocket. And so if we add more and more energy to the rocket, what we saw is that its velocity is going to get closer and closer to the speed of light, but it's not going to go beyond the speed of light. All right, so that's um, one of the postulates of the special relativity. Um, so how does that work now? Because we have an upper limit on the velocity. So we could throw more energy, and that means that what happens to what we've used in the past, which was conservation of energy and momentum, because it seems like if we have an upper limit on velocity, that's going to affect the momentum. So as it turns out, we're not going to use the same definition, or at least it's going to look a little bit different now. And our relativistic momentum is defined like you see over here. So we still have mv, so mass times velocity, but then we divide that by square root of 1 minus v squared over c squared. So you may wonder, okay, have we done everything wrong so far? Once again, it's not the case, because you can see that if we take the approximation where v is very small in compared to c, then this is negligible, and we're back to using p equals mv. Okay, so in the limit where v is actually small enough, so we're not moving that fast, the momentum is going to look like the classical version that we used before. But again, this is going to be an approximation. So the classical formula that we've used is an approximation. If we want something that's going to use for any speed, then we have to use a relativistic definition of momentum. You can see that physically it basically describes the same thing. It's we use the same units, and what you can see here is it's really mv times this factor here, and you can see that now if we increase the value for v, so as v approaches c. Okay, so just imagine we're adding more energy, and that means that the velocity of our rocket is getting closer to the speed of light. Then you can see that this is going to get close to 1. This whole thing is going to get close to 0, so it's going to be very small, which means that the momentum is going to increase. So that goes with what we know, what we've used before, and so we're okay. So again, if we look at the if we compare the classical version to the relativistic version of the definition of momentum, you can see that again, it works really well up to certain values of the speed. So here, classical momentum, which would be mv, and then now you can see that it blows up here if we use the relativistic definition. So this reflects the fact that if you increase energy, you're going to see the corresponding effect on the momentum. So again, for the most part, what we've seen before were things that were not beyond the space. So we were looking at things that were still in a realm where classical models were working just fine. But as we start considering objects that are going to move faster than that, you can see that the classical model is going to fail us. So we have to make sure that we use the relativistic definition of momentum. All right, so up next, we're going to finally get to kind of the probably the most famous equation in all of physics, and we're going to look at relativistic energy, and E equals mc squared mass energy equivalence. All right, so stay tuned. Bye.